Hi everyone, it's Professor Stevens. I've got a great example for you here. It's from section 5.2, which is about binomial distributions, but I am going to do one of the problems that actually is a 5.2 question, but it really is using skills that we learned in chapter 4. And I'm going to tie it together with what we're learning in chapter 5 so you can see the connection. So let's read this together first. Multiple choice questions each have 5 possible answers, one of which is correct. Assume that you guess the answers to 3 such questions. Use the multiplication rule to find the probability of correct, then wrong again. Now, using the multiplication rule, we would start with, let's see, P of CWW would be equal to, let's calculate each probability separately. So the probability of correct on the first try would be 1 out of 5. The probability of incorrect or wrong on the second try would be 4 out of 5 wrong answers, and 4 out of 5 again. And so the probability of getting correct then wrong would be the product of these 3. Okay? So that's how you do it using the multiplication rule. And then for part, let's put that answer in there, 0.128. Okay. Then part B says, beginning with CWW, or correct, wrong, make a complete list of the different possible arrangements of one correct answer and 2 wrong answers. Then find the probability of each entry in the list. Okay, so we started with correct, wrong. Now it's interesting that they've already put together the different ways that you could have one success, one correct answer in 3 tries. They started off with correct on the first try, then correct on the third try, and correct on the second try. So let's calculate each one of those. So now if I'm going to do the probability of wrong, correct, that would be 0.2 times, oh wait, is it wrong first this time? Yeah, 0.8 first for wrong, times 0.8 again for wrong, times 0.2 for correct. And then if I do wrong, correct, wrong, it's going to be 0.8 times 0.2 times 0.8. Okay, so this is explorative, or an exploratory exercise where you're supposed to realize that, hey, it doesn't matter where that one correct answer is in the first try or the third try or the second try. I get the same probability every time because when you multiply, it's commutative, meaning you can do the multiplication in any order. Okay, so then the probability of exactly one correct in 3 guesses is going to be, let's say, the probability of correct, wrong, or wrong, correct, or wrong, correct, wrong. Okay, and since that's an or question, I'll put the equals over here so it doesn't think I'm calculating. So since that could be translated as an or question, we could use the addition rule. So then we would say the answer is the sum of all those individual probabilities. And so that's the answer. So here we'll put 0.128, 0.128 for part B, and then the final answer should be 0.384. Whoops, gotta get in the box. 0.384. All right, now, did I put the instructor tip on here? That's not what I wanted. Okay, so I put an instructor tip on here. It says, can the binomial probability formula be used here? Check the 4 requirements of a binomial random variable and try to determine what n, x, p, and q would be. Use the binomial probability formula to verify your answer in part C. Okay, so I might have to do this all over again. No, it should, oh, now they're doing 1 and 4, so now we can do the problem over again if we're interested in that. But what I want to show you is how we can use the binomial probability formula to get this answer right here. Instead of calculating these all using the multiplication rule and then combining them using the addition rule, we can go this way. We can say, okay, so what are the requirements of a binomial random variable? If x is a binomial random variable, then the following would be true. There is a fixed number of trials. There are only 2 outcomes per trial. We have independent trials, so that the probability of one trial doesn't affect the probability of the next trial. And we have constant probability of success in each trial, meaning that the probability for, in this case, of getting a correct answer is always 1 out of 5 in all 3 trials. All right, so here our fixed n would be n equals 3. Since we're doing 3 questions, we have to give an answer 3 times, so that's n equals 3. So we do have a fixed number of trials. There are only 2 outcomes per trial. Yes, correct or wrong, right? Independent trials, yes, if you choose the correct answer on the first try, randomly, just by guessing, it doesn't make it any more or less likely that the next one you pick is going to be correct or wrong. It doesn't change the probabilities. So yes, we have independent trials. So I'll just write here a correct guess does not affect the probability of the next event, or even or for that matter, a wrong guess doesn't either. Constant probability, yeah, I already said that, right? The p is 1 out of 5 for each question. So what is little p? If you haven't watched any of my previous videos, or if you haven't done any of the filling in the slides for the 5.2 section, you might not know what little p is. Little p stands for the probability of success. And in this case, that would be the probability of a correct answer, since we're counting how many correct answers we can get, or since we're looking at the probability of getting exactly 1 correct answer, that means, in our view, correct would be success. It's not because we like to be correct, it's because we are trying to calculate the probability of being correct. So that makes it a success. All right, so this is a binomial. All of these check. So then if we can figure out what n, p, or n, x, p, and q are, then we can use the binomial probability formula. So n is obviously 3 trials. X is, since we're trying to find the probability of exactly 1, x is going to be 1. Probability of success we know is 1 out of 5. And we know the probability of failure is 1 minus p, or 4 out of 5. Notice that p and q always add up to 1. All right, so you could also just make this equal to 1 minus p. That works fine. And then to calculate the probability of x being exactly 1, using the binomial probability formula, we'll use the Excel version first, and then I'm also going to show you how to calculate it using the traditional formula from the textbook, because you will be asked to show your work. So you do want to be able to do it this way, and you also want to be able to do it on paper with the formula. All right, so Binome Distribution, the number of successes is the first thing we're asked for here. Number S means the number of successes, so that would be x, or you could just type in the number 1. The number of trials is 3. The probability of success in each trial is 0.2. And we don't have to tell it Q. We don't have to include that anywhere here, because the formula is already programmed to subtract 1 minus p to get q. So that happens automatically. And we want to say false for cumulative because we're not interested in 1 or 2 or 3. We're interested in exactly 1. So we don't want cumulative. So we're going to choose false. You can also type a 0 right there, and that will be read as false. All right, so here's our answer. Look, it's the same. Yay. See, cool, huh? Makes life a little easier if you know how to recognize a binomial random variable. All right, something else that is cool. If we look at this side from the perspective of just a random, how am I trying to say this? If we look at this side as just a generic probability distribution, where x is the number of successes, then x can be 0, 1, 2, or 3, since we're doing 3 questions. So you can have none correct, 1 correct, 2 correct, or 3 correct. So that's the exact number of successes. And then the probability of each one of those, you would have to calculate p of x. That would be the probability of all wrong. So that would be 0.8 to the power of 3. And this one we already calculated right here. And the probability of getting through all correct is easy to do. So correct 3 times would be 0.2 to the power of 3. And exactly 2 correct would mean that only one of them was wrong. So we could do the same thing we did right here, which is basically, well, another thing to note here is I added these up, but that's the same thing as doing 3 times just one of those, right? So since there are 3 positions for a wrong answer, I could do equals 3 times the probability of correct to the power of 2, because I'm going to have 2 correct ones, so 0.2 times 0.2, and then times 0.8 to the power of 1 incorrect answer. And this 3 over here takes care of whether it's going to be in the first position, the second position, or the third position. All right, now, if I have done this right, I get a total probability of 1. Cool. And all of these should be between 0 and 1, which they are. Okay, so now this is a legit probability distribution. And from here, what I want to show you is how to calculate the mean and standard deviation. So to do that, you have to know a couple things. You have to know the formula for mean. So let me show you. So for a probability distribution, the mean, notice that I'm not using x bar here, I'm using the Greek letter mu because this is for a population parameter. Remember, when we're dealing with random variables, we're talking about what could happen with the true population, not what did happen with a sample. So we're looking at population parameters here, not sample statistics. So the mean, also known as the expected value, that's another term for it. So you'll see questions where you're asked for the mean and questions where you're asked for the expected value, and they have the same formula, which is the summation of x times p of x, just like that. So what that means is that let's go back over to Excel, you take each x value and multiply it times its probability value, and then add them up. So that's easy enough. We can just do this times this, copy the formula down, and then sum it up. So I'm getting an expected value or a mean of 0.6. Let me just make sure that I'm showing enough places. For measures of center, it's always one place more than the original data values. So yeah, we're good. Okay, so that's my sample mean right there. Now that works for any random variable, when you have a probability distribution that works for any, it doesn't have to be binomial. For any discrete probability distribution or any discrete random variable, you can do this right here, and get your sample mean. Or I meant to say your population mean, mu. Now, if it is binomial, which in this case we do have a binomial random variable, there is a shortcut that is very useful to know about, and that is n times p. So now let's just see if we get the same answer by simply doing n, which is 3, times p. I mean, it's not difficult math. You can already see it's going to be 0.6. All right, so we got the same answer here just by that simple calculation, which only works because these 4 requirements are satisfied for our random variable. Yeah, and so x, just so you know what x is defined to be for this example, x is always the number of successes in n trials. Here, x is specifically the number of correct guesses in 3 trials, or three questions. 3 questions. Okay, so there's also not just the mean, but there is also the standard deviation and variance. So I'll go, this is the population parameters of a discrete probability distribution, and that was the mean, and then there's the variance, which is sigma squared, which is the summation of x minus mu squared times p of x. That might remind you a little bit of how we calculated this sample standard deviation back in chapter 3. And then the population standard deviation is the square root of the variance. So when you see it written out formally, it looks like this, all under a square root sign. And then for binomials, if it's binomial, it's NP, only if it's binomial though. Not all discrete probability distributions are binomial. And then the variance is NPQ, and then of course the standard deviation is just the square root of NPQ. Okay, so let's test that out with Excel. Okay, so now that I have, I'm going to make some more room here. So now that I have my mean calculated, I'm going to calculate the x minus the mean squared, and then times p of x, so I can add those all up to get my variance. So that'll be the x value minus the mean, F4 to make it absolute, to the power of 2 times p of x for that x value. Oh no, p of x over here. There we go. That's what I want. And copy that down, copy the sum over, and so my population standard deviation, or rather this is my population variance. population mean is this, population variance is this, and my population standard deviation is the square root of this. Okay, and let's just see over here under the binomial side, the variance, which, let me just redo this, the mean, which is NP equals this, the variance, which is NPQ, is equal to this times Q, or you could do the whole thing, N times P times Q. And there you have it. You see it's the same. And then of course the square root of that is going to be the same as this. So, I don't know, pretty cool, right? So there's our little answers, or answers to, I mean, the question we were working on didn't require us to go that far, but it's better when you can tie everything together. Homework questions tend to be piecemeal, just to make them easier to score and so that they don't feel too overwhelming. But the more that we can understand how everything fits together in the big picture, the better. And so that's what I have for you for this video. I hope it was helpful, and I will see you in class. Take care.